All right. Hello. How's it going? Hey, hi. Happy Wednesday, everybody. Thanks for coming out to Abandoned Building and having a beer with us. So if you don't know me, my name is Kirsten Nordstrom, and I'm a professor of physics at Mount Holyoke College. And I kind of run this. So if you want to find me, Google me and email me. That's totally cool. I always take suggestions for speakers and all that sort of jazz. Who is new to SciTech Cafe? Who has, yeah, welcome then. Let's get some applause. Yeah, all right. So, there will be a Q&A after the talk, and there will be some fabulous prizes there. If you have not signed in, please sign in. We need to keep track of attendance. That also enters you for the prizes. We'd also like to thank our host today. So Abandoned Building Brewery, we have the brewer and owner Matt, who's somewhere, there we go. Matt, bartender Deanna, please order some beers from her and tip her, yay, awesome. And we have our speaker. So our speaker tonight is Aaron Rubin, who's a lecturer at Smith College in engineering. We're gonna hear about ground penetrating radar, what might be we use it for, and what the heck is up with empirical models. This is all about Aaron. I think he's gonna give this in his talk, so I'm not gonna read out this block of text, but if you would like to very quickly, go for it. And 3, 2, 1, go. Our next talk is in May, so May 31st, so our last Wednesday in May, and that will be on the topic of breast milk. So Professor David Sella of UMass will be talking about breast milk and microbes and all that fun stuff. So if you're ever curious about what's the deal with that, he's going to be talking about it. So please come to that. So that will be our final event this season. We'll start up again once the school year starts, probably in September. If you want to get on our mailing list, that's the best way to get our announcements. We also have a Facebook page. We are supported by the National Science Foundation, so thank you for paying your taxes, and thank you NSF for promoting outreach and education to people who are not scientists, or I'm sure there are some scientists and engineers in the audience who just want to learn about something else aside from their own research. Here's a QR code if you want. We do have facebook.com/SciTechCafe. SciTechCafe.org, there's a link to sign up for our email list directly. You can get all the information there. I'd also like to thank my coordinator, Lauren Engelbrecht, and our assistant, Midge Hartshorn, who are over there. Let's give them a round of applause. And I don't think I forgot anything, so please remember to drink some beer, support our hosts. Please remember to think of good questions, and you will have a chance to ask them at the end of the talk. All right, so let's welcome Dr. Aaron Rubin.
Thank you. Great. Can you hear me okay? All right. So as promised, I will give a brief introduction of who I am, how I got into ground penetrating radar. You can see me in my first slide. I got my undergraduate degree from Tufts University. I was actually a mechanical engineer, played a bunch of Frisbee, hair was long, things were good. When I entered, I was like, you know what, I'm gonna be an electrical engineer or maybe a mechanical engineer. Took circuits and said, I'm gonna be a mechanical engineer. But as things went along, I said, you know what, I'm not sure if I wanna be a mechanical engineer. So after that, I went to UMass Amherst and got a master's degree in civil engineering. And I said, I like soils and I like building in soils. So I became a geotechnical engineer, someone who is involved in large civil engineering, infrastructure-y kind of projects, anything that's kind of big and has to do with the earth. After UMass, I practiced as a professional engineer for 6 years at CDM Smith in Boston, and did a lot of traditional geotechnicals type work, building foundations, did some geothermal work, that kind of thing. And that's where I got my first sort of inclination about GPR, what it is, and all that. And I have to tell you, I was a little bit of a skeptic. During this 6 years, I was sort of like, I don't know about this stuff, seems kind of hand-wavy, unclear. After working for about 6 years, I said, okay, I'm gonna go back and get a PhD, and then I'm gonna enter academia. But before I started my PhD, I had a really great opportunity to work with some folks at UMass on an archaeological dig in Tuscany. And being an engineer, right, I figure you have a whole summer off, you've got to do something fun, right? Being an engineer, I was watching these students dig a 5 foot by 5 foot trench, for 3 or 4 students for the entire summer. And I thought, like, there's got to be a better way to do this, right? So I started thinking about some of these geophysical technologies, how we could use them. And this really got me thinking about GPR more at a fundamental sort of physics level. And so for my PhD, I did a lot of work sort of thinking about how we can use GPR within civil engineering and particularly within geotechnical engineering. And that has continued after my PhD to my time at Smith. I've been there for 5 years now, and I've continued doing some GPR type research there as well, in addition to teaching juniors and seniors. And as long as we're talking there, I got a plug. I teach the capstone course for our senior engineers at Smith, and they are giving their end of year presentations this Friday from about noon to 5 in the campus center. Open to the public, so if you're curious what they might be doing, they're gonna be talking about projects they've worked on all year for their senior capstone. All right? So what are we gonna talk about today? First, I'm gonna talk about what actually is ground penetrating radar and how does it work. Then get a little bit into what do we currently use it for, some of its common use cases, and then start to be a little bit more forward thinking about like, okay, now that we know what it is, now that we know how it works, what's the potential for this technology? What could we be doing with it? And then at the end, I'll tie a little bow on it and I'll talk a little bit about empirical models and why engineers love them so much and some of the pitfalls that are out there, but some of the reasons we love them anyway. All right. So what is ground penetrating radar? It's radar for the ground, of course, right? Obviously. But what we would say more typically is that it's this non-intrusive geophysical method that uses radio wave pulses to produce images of the subsurface. Right? Again, kind of technical, but basically what that means is we let radio waves propagate into the ground and we try and see what kind of information comes back. And then depending on who's used it, we try and interpret those results in a useful way, right? So let's take a step back and remember that radio waves are on the light spectrum, right? So if we have these short waves, X-rays, gamma rays, ultraviolet, those are the things that we don't want hitting our skin, they're bad, right? Then we have visible light in here, and then all the way at the far long wave of the spectrum, we have these radio waves that we use in our cell phones, our Wi-Fi, radio towers, right? If you're listening to your car, radio waves, right? Been around for over 100 years in terms of our usage, so this is not exactly new technology. And if we think about what we know about radar, right? We have this little picture, satellite dish spits out some radio waves, hits an object, comes back. Note that when we send it out, it's a really high amount of energy, and then it comes back with some lower energy. It's gonna be important later on. When we're doing ground penetrating radar, we have the same basic setup where we still have our signal antenna, and we have a receiving antenna, and the signal antenna is gonna send out a radio wave pulse, and we tend to think of that as wave fronts, sort of as this propagation of this radio wave as it spreads out into the earth. And sometimes we'll talk about them as ray paths, sort of thinking of it as a direction where it goes out, hits something, comes back again, right? And what we actually see is something that looks like this. This is what we technically call a squiggle. And you can see that the first return is a big squiggle, and then later returns end up as smaller squiggles. Because as this wave propagates out, the energy is becoming diffuse. We're lowering our amount of energy as we go deeper into the ground, right? And so we get sort of a less strong response as time continues, and eventually we just have background noise and we can't really see anything else coming back. To illustrate what happens when we produce one of these squiggles, you can see we've got this waveform here, and it's going to hit this barrier that's representing a change in material. So we're going from one material to the next material. And what you're going to see is that it hits that surface, some of the energy bounces back, some of the energy keeps going forward. Something like that. The other thing that you might not quite have picked up, but I want to highlight, is that when this piece right here enters that new material, it actually slows down potentially, right? So if it's traveling in the air and then it hits the earth, we actually have that radio wave slowing down, which is kind of weird because usually we think, hey, light travels at the speed of light, right? We have, oh, this is the c right there, it's in this little equation, right? That's constant. But that doesn't mean that radio waves travel at the speed of light regardless of what material they're in, okay? So when we're in the earth, how fast that wave is traveling is primarily a function of this material property, which is called relative permittivity. So that relative permittivity ends up being an important material property for estimating something like depth, right? Because if we look at what these signals all look like when we stack them together, right? Squiggly line, squiggly line, squiggly line, and we keep moving forward. Say if I'm walking along, right? We can keep taking these measurements, and if we notice something that's consistently happening, we can start to infer what might be in the subsurface. The problem, or at least one of the problems, is that this axis is not depth, it's time. It's how long did that signal take to come back to the receiver. And so we have to estimate what our relative permittivity is to figure out what the velocity of that wave was to figure out how deep the thing was, right? So this is sort of a big problem in that, okay, we know that there's something there, but we don't know exactly how deep it is. That kind of defeats part of the purpose, right? So this is a problem that we have to deal with. We'll circle back to how we can maybe solve that problem. So what do we use this for? Generally speaking, we have two main objectives if we're using GPR. One is object detection, so there's something in the ground, we want to try and find it, or maybe it surprises us that we weren't expecting something, but we saw something, right? So that's sort of one general area. And then the other is to try and understand these sort of macroscopic features where we're moving GPR in different locations and we're seeing trends, right? So if you're in the geosciences, some of those macro features that you'd be looking for is, say, groundwater, right? The electrical properties above and below groundwater are going to be pretty different. That's going to show up in GPR. Say you were on a glacier, right? You wanted to know how thick the ice was in that glacier. You could use GPR to give you a measurement of that. You could identify bedrock types and layering and fractures and that type of thing, right? These big sort of systematic changes in the subsurface. In engineering, objects, pipes. You want to know where a pipe is? I can't tell you how often when I was working as a civil engineer, you'd go out to a site and they say, hey, there's a sewer line in this street. You say, great, this street is 50 feet wide and it's a 5-foot diameter sewer. I'd like to know where that is before I start digging, right? Utility location, really, really, really common usage of ground penetrating radar. Other things you might find is other kinds of obstructions, old rail lines, old building foundations. It's amazing what people forget about is actually down there. And then on a macro level, identifying for sort of structural condition. So how good is the pavement, say, below what you can see? What's that subbase look like? For concrete, we can use it to see if there's internal cracking that might not be visible on the surface, or to identify what kind of metal is used for the rebar in that concrete, that kind of thing. And in environmental engineering, we can detect contamination plumes in the ground. Again, we're sort of looking for differences in electrical properties. In archaeology, which is where I started thinking about this stuff, we can use it to find building foundations. We can use it for forensics to find old graves, cemeteries, that kind of things, and old other features that you might encounter like wells, roads, filled in canals. Really anywhere where you've disturbed the ground, you should see some difference in signal. And last, we can also use it for some military applications for detecting landmines, IEDs, things like that. Again, we want to know if there's some kind of an object in the ground and give us some idea where that might be. So how this actually looks in practice, let's say we've got our little GPR box right here and it's got our 2 antennas. It's a little hard to see, but we can send a ray path down and it bounces back off of this pipe. And you can see right here, it took some amount of time at this location to appear as a little squiggly line. And if we move that forward a bit, you can see now that distance is just a little bit shorter, so the time is just a bit less to get there. And we can continue going forward and continue seeing those pipes until we get right above it, and that'll end up being a peak. And if we keep moving beyond, we'll see that now it takes more time once again to achieve that same location. And so what we see in the data are these parabolic features. And so whenever we see something that's parabolic in shape in our cross-section, right, we have some idea that there's something there. It's a rock, it's a pipe, it's a who knows what, but it's there, right? And then we have to use sort of our human brains, use our frontal lobes to try and figure out what would be a reasonable explanation for what might be there. The other thing we commonly see in our data are sort of linear features, right? Imagine now instead of going directly perpendicular across the pipe, you're moving directly over that pipe. So as your GPR goes through, you keep hitting this thing at the same location. And that's useful for us to see because there aren't a lot of just straight linear features in nature. And so that starts to make you think, okay, this might be man-made. Similarly, we can have soil interfaces. Again, it's a little hard to see here, but say you're bouncing off of this interface and bouncing off of this interface, we can see different geologic layers that come up as linear features. So what does this actually look like? You get something that looks like this, right? And so when you see it for real, you're like, oh, what the heck is going on there, right? But it turns out we see some linear features. So there's a linear feature straight across here. That's that water table. And then right down here, that's a soil interface layer. You can see some differences in attenuation, where how much energy is coming back, where we have a lot of energy and then a much less energy. And a whole bunch of these parabolic features, which in this case are boulders in the ground, right? So it takes a little bit of art to start to identify what some of these features are and a little bit of experience. Here's another set where this is my parents' garage. And when I was a PhD student learning how to use GPR, I said this could be a fun place to use GPR because I remembered when I was a little kid in the 90s, they used to have this terrible sloping driveway, right? Get filled with snow and cause them all kinds of problems. So they built a new garage and they flattened it all out. But if we look along this line right here, which is this data in the upper right, there's these big parabolic feature, which is actually the old driveway still visible below. And then if we look at this line that comes down through the driveway, there's this line that is actually the old driveway as well. A little hard to see, but there's a bunch of parabolic features right here, and that's actually the sewer in the street. All right, so what are some limitations? Let's say, again, we have this signal and it hits something where all of the energy comes right back to us, right? This ends up being a little bit of a problem because then we're not gonna see anything below that feature. This tends to be, for example, clay minerals are highly conductive and act as sort of a mirror to all this energy. We also see that metals, so if there was a metal plate in the ground, that would sort of stop anything from penetrating. And actually some types of environmental contamination can have this same effect, where we can sort of identify where they are because we can't see anything below them. The other issue is eventually all of our energy is gonna dissipate, right? We can't see infinitely deep into the ground. And so generally speaking, we have a little bit of a conundrum in that the lower the frequency is, the more deeply we can see into the earth, but the less our resolution is gonna be. Meaning, sure, we could go and see 100 feet into the ground, but we're only gonna see objects that are roughly the size of a boulder. By contrast, we could pick a really high frequency and we could use it on concrete and we could see features that are millimeter in size, right? So we have this trade-off between how deep we can go and what we can actually see. So let's talk a little bit about what we might be able to do now, right? This is kind of what we do. This is sort of the timeline of GPR equipment, and this middle picture right here, that's really where we're at right now. So if we're using GPR equipment, we've sort of moved beyond this stick method where you have to pick it up and put it down every time you want to go forward, right? And the main reasons for this is that this kind of technology is what we're using in the 90s, and now we have computers, which has allowed us to do several things. First, we can collect a lot more data. We used to actually just be limited in terms of what we could actually record in the 90s because our hard drives weren't big enough to record more data. So we can now record hundreds of traces as we're moving along instead of, say, dozens of traces, dozens of radio waves, right? The other thing that's happened is we now have batteries where we can take this stuff out and we can use it all day, and we can put it on one of these little carts and push it around, and little tablets that can actually show us in real time what we're seeing in the ground, right? And that's what we're doing right now with it. Because again, our computers have become fast enough to do real-time processing of the data we're collecting, right? And usually just in this little box right here, we have 2 antennas, and that's sort of the current state of things. But this harkens back to that problem of not knowing how deep we are, right? We still just have time as our vertical axis. And so one solution that we've started to move towards a little bit is this ATV kind of thing, and this has 16 antennas on it instead of just a pair of 2 antennas. And what that allows us to do is to add more simultaneous equations so that we can triangulate how deep that signal is amongst a whole slew of antenna. The big benefit is it allows us to produce images like this on the left. And as you can see, these square foundations become more and more apparent as we go deeper with these horizontal slices, right? So this is going from like ground surface down about 7-ish, 8-ish feet into the ground. And we can produce some really highly detailed results with this. And if we're thinking about this for the kind of simple-ish math of it, again, we used to say if we only have 2 antennae, we don't know velocity, we don't know this material property, that's a problem. But now if we have all of these multiple antennae, we now know depth from this triangulation of multiple readings going through the same things. And we know what time is because that's what we're measuring with our GPR to begin with. And so if we know depth, we know the relative permittivity. And you know this must be exciting because I've put so many exclamation points after this, right? And you're like, okay, but why do I care about relative permittivity? And the truth is you don't. It is a useless material property for engineering. Really not much we can do with it. But the relative permittivity is not just random, right? It's gonna be a function of things we do care about within the soil. So it's gonna be a function of how much water is in the soil, what's the density of the soil, what's the mineral makeup of the soil, which all are things that are practically useful to a geotechnical engineer. So if I might take you on a quick excursion about railroads, right? Derailments in the news. I've even got some pictures of stuff. These are from actually like 3 years ago, so they're constantly in the news. Every year or so we have a big derailment that makes the news. But there's actually probably 3 to 5 derailments in the US every single day. Literally thousands a year. You don't hear about them because most of the time, this is kind of a minor thing. The crew goes out there, they pick up the train, they put it back on the rails. No big deal, right? And every once in a while, it goes up on Google, right? So one of the big problems, and you'll see it right here in this video, is what engineering railroad folks call mud spots. And just as it sounds like, particles infiltrate this railroad ballast, which is basically just crushed stone, and it starts to fill in that void space like I've shown in this top figure. And what happens is when all that void space gets filled in and when it gets muddy with water, you'll see that you start to have a lot of movement of that rail system, right? So as you can see as this going by, those metal rails are moving up and down, and you can kind of understand how that could become misaligned and cause a derailment. The danger of this is that by the time you can see it at ground surface, like this mud spot here, it's already dangerous. We're already in a situation where a derailment could occur. And so for a fairly long time, people have been taking GPR out on the railroads and trying to qualitatively see if anything changes, right? They look at the GPR scans originally, they look at them a few months later, and they say, has anything changed 6 months after the first one we took? And if something has changed, that could mean you have a mud spot. Could mean something else as well. But if we're looking at it qualitatively, we don't necessarily know, right? So it would be really nice if you could use GPR in a quantitative way to tell you, is this railroad ballast safe? Are we worried about a derailment now, or are we in good shape? And I did a little bit of this during my PhD as well. You can see here I am. I've got my UMass hard hat. That's how you know I'm in my PhD time. I've got a multi-antenna GPR, and we were trying to think about, can we use this knowledge of relative permittivity to tell us something about the state of ballast, about this crushed rock? And I've continued this at Smith. You can see we did these box tests with railroad ballast and mixed in fine particle to simulate that mud problem, and then we filled them up with water and we did a bunch of testing with GPR on them. And we made a big mess, and it was great. Got some good experiences. And so we came up with some data. And what we found is, as you'd expect, there is a relationship between our measured relative permittivity and the water content. And this kind of relationship has been observed since about the 80s. There's nothing new to GPR, but we're just doing it on railroad ballast. And we look at this and we're pretty happy. We're saying, okay, we're probably collecting good data, because this is about the level of correlation you'd expect. Because in the last 40 or so years, we've realized that it's not just water content that matters. It's density, it's mineralogy, it's what have you. We've come a long way, or at least so we'd think. If I look at this chart, this shows how our existing models predicted the relative permittivity that we measured. And as you can see, it's not great. We're using this Top et al. Model that was developed in the 80s and is these diamond shapes. And the square shapes is a CRIM model that we developed about 5 to 10 years ago. I use the royal we. Engineers develop these things, not me personally. The problem is that in 40 years, we're seeing really incremental change in the models. And part of the thing here that I'm gonna kind of wrap up with is this idea of empirical models versus analytical models, right? These are empirical models. This original Top et al. Model, they did exactly what we did here with sands, and they put a trend line through it, and they said, great, we now can predict the relative permittivity based on volumetric water content, and it's got some plus or minus to it, and that's fine, right? That works quite well with sands, and if you use this CRIM model, it works really well in sands, right? But we're not testing with sands, we're testing with big chunky ballast, and clearly there's something that isn't quite adding up, right? So we say, okay, our empirical model is bad, right? And as someone who studies models, I tend not to think of models in terms of good or bad. The engineer in me says, is this a useful model, right? And so what I mean by that is, during my PhD, I was thinking about empirical models as well, and I wanted to think about if we could connect the relative permittivity of GPR measurements to thermal conductivity, right? I was thinking about geothermal and how can we do some site investigation for that. And I produced this nice chunk of data, which shows pretty good at this lower end and pretty good at this higher end, and kind of not so good in this middle part, right? So this kind of poses the overall challenge of I would love to come up with an analytical model that perfectly describes the relative permittivity, right? And perfectly describes the thermal conductivity of soils. The problem we run into is that we've been studying this stuff for 50 or 60 years and we don't have those analytical models, right? So why can't I quit empirical models? They clearly have some problems, right? And so now coming back, engineer hat me, not necessarily research me, says, okay, well, I want to try and solve this problem of train derailments, right? That analytical model that might work on sands and gravels and clay and everything, that might be another 20 or 50 years away, right? So this is why I kind of think as engineers, we get stuck a little bit with the, well, it's 10 or 20% off, but that's pretty good, right? It's good enough for now, and we'll keep working at it and we'll try and get better at it. All right, so that's where I'll leave you at for my talk, and we'll open it up to some questions about ground penetrating radar.
All right. Ooh, hot mic. All right. Thank you, Aaron. That was lovely. I never thought I'd say ballast was lovely, but I study similar materials, so I can say that it was lovely. So we are going to open it up to Q&A from the audience. So I'm just going to wander around with this mic, and any questions go. Just keep them respectful, all that sort of stuff. Anybody? Who's going to be brave? All right.
This is maybe outside the scope of the presentation, but do you know if there is any effect on doing ground radar on animals or like insects or plants or anything the way that like sonar has on whales coming from a submarine or something?
Yeah, that's a good question. The good news is no, right? The frequency ranges that we're using with these radio signals are things that we and animals are exposed to every single day through our phones, through the radio, right, in our cars, all of that. Fortunately, it's at a low wavelength where they would not be even aware of its presence.
Okay, other questions? All right, I see one over here, and then I see you. How is the geothermal at Smith going? Is there a timetable to shut down the boiler room?
Yeah, I don't know if I'm authorized to say anything, but I think it's probably going good. If you've been on campus lately, they're starting full steam ahead with construction, and I think they're going to start putting in wells in this summer, actually. I don't know when they plan to shut off the boiler, but I know that the full stage geothermal is well on its way.
All right, we have one over here. The mic went dead.
Is this used at all to search for fuels like oil or natural gas? I'm surprised that wasn't included.
Yeah, it's probably not used so much in the petroleum industries, primarily because of the depth issue, right? Usually when we're talking about where oils or natural gases are, we're talking about thousands of feet below the surface. And realistically, the technology is good down to about 100 to 150 feet.
Okay, we have another one over here.
So what's the frequency range and like the RF power levels typically? I imagine you use different frequencies depending on where you're trying to measure.
Yep. So the frequency range, if you're going down 100, 150 feet, you're probably talking about like 50 megahertz. And for most sort of civil engineering, archaeological applications, you're probably in a 400 to 500 megahertz range. And then if you're talking about any of that sort of concrete inspection, you're kind of in a 1 to 2 gigahertz range. And so overall, you're talking 50 megahertz to a couple gigahertz is the frequency range you're talking about. And I honestly can't remember the power level well off the top of my head, because it turns out not to be a huge factor in terms of things like depth of penetration or resolution. You sort of lose that energy proportionally. So if you put more power into the system, you just lose that power faster. So the frequency range is sort of the big thing that dictates application.
There are a lot of cases where when 2 measurements don't work, 16 don't work just as well. So can you explain why it is with measuring depth, why 16 towers gives you a better measurement than 2?
Yeah, sure. So it comes down to sort of your simple 1 equation, 2 unknowns kind of part of the problem. And I admittedly glazed over this a little bit, but essentially if you send out a signal and then get a location reading from that signal in 16 different places, you can do a simultaneous equation solve for what the depth would have to be for it hitting off of the same feature. So when you go up to 16, it really gives you a pretty high confidence of what that depth was and what that material would have had to have been in terms of its relative permittivity property in order to sort of solve out those velocities and depth problems.
Okay, other questions? Okay, ooh, all right. Whew, getting my steps in. Okay. You do, everybody does.
I have 2 separate questions.
Sure.
The first is, I drive a Subaru
Mhm.
with eyesight, so it works on the principle of looking ahead and seeing silhouettes of things and figure out what they are.
Mhm.
Is it possible to do algorithms with this ground penetrating radar to actually figure out over time, after seeing many different things in the ground, what you're actually looking at instead of having to use art as to try to figure out what it is? And my second question is it possible to use drones with ground penetrating? Say, if you're looking for mines, per se, that you don't want to actually go over the ground, can you, if they're thinking of using drones with ground penetrating so you don't actually have to walk on the ground?
Yep, yeah, those are 2 good questions. To the first one, there are sort of people on the software side of ground penetrating radar who have been trying for a really long time to get computers to automate the detection process and tell you, oh yeah, that's definitely a pipe or that's definitely a rock. It turns out just to be a really tricky problem for computers to solve, in part because the data for the 2 objects, a pipe or a rock, looks similar. But perhaps with some of the more advanced AIs that have been developed recently that have been sort of all over the news, they might be good-ish or maybe better at doing that, particularly if they knew more about the target area, right? A lot of times you sort of infer like, oh, I'm in a road, I'm seeing this signal repeatedly in the road, that's probably a pipe, right? And so we're sort of using our sort of reasoning skills to figure that out, which is sort of a challenge for a computer to do based on just seeing an image. To the second question about detecting landmines with a drone, yeah, that is actually done. And there are all sorts of studies sort of trying to optimize that problem in terms of how high does the drone need to fly in order for the signal to really get down there and then come back again, and what frequencies are best to use. But that's definitely an active area of research.
Okay, we have a question over here. I'm over here.
What is the difference between analytical and empirical?
Good question. So empirical is kind of the easier one, so I'll start with that first. Empirical is we collect a bunch of data and we sort of throw it at a wall and we just try and trend line the data to see if we see any trends happening. And we don't necessarily think super deeply about why that trend might exist. On the flip side, the analytical approach is to try and come from the other side and say, we know some stuff about physics. Let's start with our calculus equations in those physics and try and solve them for this problem to end up at that equation, right? So in many ways, if you can come up with the analytical solution, big picture, that's more meaningful from a what do we know about the Earth and its physics kind of perspective, right? But it's also a much trickier problem to solve, and some of those problems don't actually have solutions. Like literally, like there isn't a mathematical answer. So that is kind of troublesome when you're trying to solve something and you don't even know if there's an actual solution to it, right? Whereas the empirical one is like, great, let's put this into Excel and plot it, right? But it ends up being sort of less broadly meaningful.
All right, other questions? Yep, okay.
Over the years, has there ever been anything particularly strange or mysterious that you found?
I don't know that there's anything necessarily strange or mysterious that I found. Although I do have a good story about something that was not found. So I'll go that direction instead. One of the reasons I was a skeptic about this technology was when I was working as a professional engineer. This would have been about 10, 15 years ago. Do folks remember that there was that big water main break and Boston lost water, right? This might ring a bell. It's like a decade ago-ish. Well, our firm was one of the ones that was sort of tracking down the reasons for why this might have happened. And so they wanted to find the components of this pipe and the sort of containment buckle that broke. So they sent out some GPR to the site, and the GPR guy was like, 20 feet down, there's a metal signal right there. And so they dug a hole 20 feet down, and they didn't find anything. And so then, me being a junior engineer, they said, go down into that hole and start poking holes until you hear a big clang. And so I spent a week in a hole driving rods into the ground and did not find anything. And it turned out the clasp they were looking for was a couple 100 yards away. So I was a little bit of a skeptic from then on, but it eventually won me over.
Other questions we can probably take. Oh yeah, here we go, in front.
I'm just curious, you talked about archaeology in the beginning. Is this a pretty common tool that's used in sites?
So I wouldn't say it's a common.
Can you repeat the question?
I was asking about archaeology and if this is a common tool for discovering sites or working on a site.
So I would say it's common if you have the money, right? And so this ends up being a little bit of a good learning for me before my PhD, was to really gain an appreciation for the shoestring budget that a lot of the liberal arts faculty are on when they do a project, right? It's sort of a different level of monetary resources. So absolutely GPR can work very well for archaeological investigation. And that 16 antenna guy was primarily created for archaeological investigation. But that 16 antenna guy also costs like $250,000. So most digs are not going to have the resources to purchase something like that, and realistically are probably not going to be able to purchase, say, a $20,000 or $50,000 piece of equipment either.
Oh yeah, let me.
Blanking, there was a book we read a while ago, I think called The Lost World Kingdom of the Monkey God, and they talked about LiDAR. So what's the difference between?
No, that's a good question. Yeah. So you might have seen in the news where they do these LiDAR surveys over the jungle, and they expose sort of pyramid structures in sort of the Maya Aztec down into the Inca areas as well. And the key difference there, although there are lots of similarities, is LiDAR uses lasers and GPR uses these radio waves. And so if you have LiDAR, it's very directional. It's like you shoot a beam of light and it hits something, and you have sort of a range finding based on that beam of light. And lasers don't necessarily do a good job of penetrating into the ground. So you're really getting a surface measurement. Yeah, and what's really useful there is because they're not going into the ground, you know that that laser is traveling at the speed of light because it's going through the air. And so you're able to get this contoured surface with the LiDAR and then in a processing fashion very similar to GPR, you can sort of remove all of the scatter of the vegetation to just get your lowest measurements.
Very cool. One or two more questions? We have them? Who's the crazy person filming the train?
This guy.
Okay, one more.
If there's that expense, are there companies that own that equipment that you can hire to come in for a day, or do you actually have to purchase that equipment?
Yeah, there's companies that we'll rent the equipment to you, or we'll do the measurements themselves. Most sort of geophysical kind of testing companies probably have some form of GPR in-house, in addition to a whole range of other ways of measuring into the subsurface.
Okay, any last questions? Oh, Midge, yeah.
I was just wondering, how distinct does an object have to be from the surrounding material in order for you to distinguish between signal and noise?
Okay.
I can repeat it. So it's the question is, how distinct does the difference in material have to be able to detect it? And that ends up being actually a pretty complicated question because it depends. And essentially what it depends upon is how big that object is, what frequency you're using to try and detect it, and to a certain extent how deep it is underground, how much your signal has attenuated. So there's a whole ton of different factors that basically come into play there.
Okay, so I think we'll thank the speaker one more time. We will thank him again, don't worry. What we're gonna do is make the speaker go away for a little while to select, we'll do 2 best questions. Okay, and the prizes we have today, let me just do this. There's no great way to do this, but. All right, so we're gonna do, Aaron's gonna select the 2 best questions, so follow Midge over there and select the 2 best questions. And I'm gonna tap dance in front of the room for a little bit. Yay! Literal soft shoe because I'm wearing sneakers. All right, so if you signed in, you should have gotten a blue raffle ticket. Yeah? Okay. This gives you incentive to sign in. The prizes we have are LED magnetic pickup tool with a flashlight, great for auto repair, camping, boating, etc. Nice tool. These are all engineering approved prizes, by the way. We have a 6-in-1 pen multi-tool. Looks like we got a ruler, a level, all sorts of other things. And we have a Leonardo da Vinci catapult. Classic. So we're going to announce the raffle winner and the best questions. Best questions will get priority, so try to rush up here first. Let's draw for the raffle prize. Can I have you do it? I think I might have had you do it before. All right, so last 3 numbers are 559. Do I have a woo? Must be present to win. What? Did you draw yourself? I guess, you know? No? Okay. You want to draw another one? Draw another one? Okay, all right. The fix is in. 548. Do we have a woo? Woo! Not reading glasses. What were the top 2 questions?
I'm going with the question on the analytical and empirical model.
Okay, well done.
The question on LiDAR.
And the question on LiDAR. Well, there you go. Okay, so questions come up first. Select your prize. We're also going to be presenting a thank you gift to our speaker, Dr. Rubin. So thank you very much.
Thank you.
Speaking at SciTech. Go ahead and just pick whichever one you want. We will be back here on May 31st to talk about breast milk. So I know you want to talk about that. You might want to learn about it. If you are not on our mailing list, go to scitechcafe.org or facebook.com/scitechcafe and bus your tables, please. We're not employees. There are only a couple employees on tonight. So please, but there's a trash can over there. Please try to clean up, take your glassware in the main room. Please buy another beer. The brewery's open for another half hour-ish or so. Tip your bartender. Drive home safe. Have a great night. Thank you so much. Yes, I was. It's however you want to decide it.